for our last problem on distinguishable permutations, we're going to ask how many ways can I get each of the outcomes when rolling 3 four-sided dice? So first of all, what are the outcomes of rolling 3 four-sided dice? Well, on the low end, 3 ones would give us 3. On the high end, we could roll 3 fours, which would give us 12. Now, our basic knowledge of permutation says that there should be a total number of ways that I could roll them, separate ways. And that is achieved by taking 4 times 4 times 4, because at each roll there are 4 independent choices, which is equal to 64. So we're going to come up with a way to find 64 different types of rolls in 3 through 12. So first I'm going to list the numbers 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, I'm going to also list as ordered triplets the number of ways that I could get a 3, for example. Now a 3 you can only get by rolling 3 ones. So I'm going to write that like this. 1, 1, 1. Now 4, you could roll a 1, or a 2. Now think for a second. Is there this, what's the number of ways that I could get a 1, a 1, and a 2? Well, there are 3 ways. How many ways could I get a 1, a 1, and a 1? There's only 1 way. So there's a subtle difference between these two. Now, for 5, I could get a 1, and a 3. Or I could get a 1, a 2, and a 2. For a 6, I could get a 1, and a 4, a 1, a 2, and a 3, or 3 twos. Okay, if you're wondering how I'm getting these numbers, well, you could just kind of fumble about trying to find each one, but the methodical way that I do it is I look at each pair here, and I add 1 to each of the numbers. So I add 1 to a 1. That gives me 1, 2, 3, right there. If I add 1 to the third, then I get 1, 1, 4. If I look here and I add 1 to this, I get 2, 2, 2. And I just ignore any repetitions. So for 7, I can't add another 1 to 4, so I have to go with 1, 2, 4. I can go with 2, 2, 3. Or, let's see, I can go with, let's see, 7, what am I missing? 1, 3, and 3. Okay, for 8, I could do a 2, 2, 4, a 1, 3, 4, and a 2, 3, 3. Let's see, for 9, I could get a 3, 3, 3. I could also get a 2, 3, 4. Or I could get a 1, 4, 4. Now, notice that we're building up, and then we're going to start diminishing down, because there is a sort of symmetry here. So for a 10, I can only get that with a 3, and a 4. Or a 2, a 4, and a 4. An 11 can only be achieved one way, and that is with a 3 and 2 4s. And a 12 is a 4, a 4, and a 4. Well, if we count up the pairs, first of all, notice the nice symmetry here. And those who study statistics will say, hey, that looks kind of like a bell curve. It almost is. What I'm going to do is I'm going to count for each individual pair the number of distinguishable permutations for each pair. Namely, how many ways can I roll a 1, a 1, and a 1? Well, there's, like I said before, there's only one way to do that. How about a 1, a 1, and a 2? Well, there are 3 ways. 2, 1, 1, 1, 2, 1, and 1, 1, 2. So I'm going to write that as 3. For those who are curious, it's because it's 3 factorial over 2 factorial, 1 factorial, which is just 3 over 1. So 3. Now 1, 1, 2 is no different than 1, 1, 3, so we should expect 3 there. And same thing here. Same here. Now 1, 2, 3, that is somehow different, because there are 3 different ways to get it, or sorry, 3 different numbers from 3 different sets, from 3 different classes. So that means I can do this just like ordering students in a class, and it's 3 factorial, which is 6. Alright? Now 2, 2, 2, just like 1, 1, 1, there is only one way to do that. Now 1, 2, 4 is just like 1, 2, 3, there's 6 ways. And at this point I'm just repeating patterns. Every time I see 2 of one element and then 1 of another, that's a 3. Whenever I see 3 unique elements, that's a 6. Whenever I see all of the same element, that's a 1. And those are the only options I have. So this is going to be 3 as well. This is 3, 6, 3. This is 1, 6, 3. Then there's 3 and 3. Then 3 and 1. So if I add all of the things in blue up, I should get, there's only one possible way to get a 3. There are 3 possible ways to get a 4. There are 6 possible ways to get a 5. Then 10 for a 6, 12 for a 7, 12 for an 8, symmetry. And again, echoing the symmetry, there are 10 ways to get a 9, 6 ways to get a 10, 3 ways to get an 11, and 1 way to get a 12. Now, if I did this all right, and there is a way to check, I have to add all these numbers up, and that's actually not that bad. 1 and 3 is 4, 4 and 6 is 10, 10 and 10 is 20, 20 and 12 is 32, 32 and 12 is 44, 44 and 10 is 54, 54 and 6 is 60, 60 plus 3 plus 1 is 64. So all of this adds up to 64, as we knew it should. So, this is how you create a distribution for rolling dice, which will come in handy when we start talking about probability.